Hey statistics class. In this lesson, we're going to be looking at section 5.3 and 5.4. But first, let's look at 5.3. You're going to be looking at independence and the multiplication rule. Let's look at our objectives. Okay, our objectives are going to be identifying independent events, and then we're going to be using something called the multiplication rule for independent events, and then we're going to lastly compute the at least probabilities. So our first objective is going to be identifying independent events, and let's take a look at the definition. Two events E and F are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. And then the definition of dependent is two events are dependent if the occurrence of event E in the probability experiment affects the probability of event F. So in these next three little examples that I have for you, we're just going to look at these and tell whether these are these statements here are independent or not independent according to what is being stated. Okay, so part A here, it says suppose you draw a card from a standard 52 card deck of cards and then roll a die. The events draw a heart and roll an even number are going to be independent because the results of choosing a card do not impact the result of the die being tossed. Okay, so those are independent events. Now look at this one. It says suppose two 40-year-old women who live in the United States are randomly selected. The event of woman 1 survives the year and woman 2 survives the year are, again, they're going to be independent events because one woman surviving that has nothing to do with woman 2, they are not connected in any way, so they're going to be independent of each other. Now let's look at the third one. It says, suppose two 40-year-old women living in the same apartment complex. The event of woman 1 survives the year and woman 2 survives the year are going to be dependent events because they have something in common with each other. What affects one woman may affect the other. All right, so objective 2, it says use multiplication rule for independent events. So now that we know what independent events are, this is the type of rule that you will be applying on those types of events. So here's the multiplication rule for independent events. It says if E and F are independent, then what you'll be doing is the probability of E and F is equal to the probability of E times the probability of F. All right, in this example, we're going to be computing probabilities of independent events. And what is stated here says the probability that a random selected female aged 60 years old will survive the year is 99.186%. Okay. And then the question is, what is the probability that two randomly selected 60-year-old females will survive the year? So selecting two of these females are the independent events. So how I would set this up is that what we're looking for is the probability of the survival of the first female and the survival of the second female. And the way the independent event computation goes is we multiply. So the probability of the survival of the first times the probability of the survival of the second. And since each of these probabilities are the same thing, the percent up here, we will say this. That probability times it again is equal to the probability that we are looking for, which is and that's it. Here's another example of computing probabilities of independent events. It says a manufacturer of exercise equipment knows that 10% of their product are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it is purchased. If there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? So in this one, how we find the probability of what we're winning here, that what the portion of the customers that will actually make a valid warranty claim, is we assume that the defectiveness of the equipment is independent of the use of the equipment. So we find this probability here, that the probability that the equipment is defective and used. So using the independent events multiplication rule here, this is equal to the probability of the defective equipment times the probability that it is used. And then putting that together, this is the probability for the first one, and here's the probability for the second one. And putting that into decimal form, we get this times the 0.3, and multiplying that together, we get that, which if you want to turn it back into a percent, it'll be 3%. And that is the estimated portion of the customers that will actually make a valid claim on this exercise equipment, only 3%. Now, the multiplication rule for independent events doesn't just only work for 2 independent events. It also works for n number events. So if you have n number events that are independent of each other, then you can take the probability of all of those events and apply this multiplication rule just like this right here. Find the probability of the first times the second times the third, all the way out to how many ever number of independent events that you have. Okay, so going back to an example we looked at before, it says the probability that a random selected female aged 60 years old will survive the year is 99.186%. But this time, instead of computing the survival of 2 randomly selected females, it's asking us what is the probability that 4 randomly selected 60-year-old females will survive the year. So just like 2 people who are female surviving the year, it will be all 4. So the probability that all 4 survive is equal to the probability of the survival of the first and second and third, number 3 there, and the fourth, which breaks down to the multiplication rule here. We have probability of the survival of the first times the probability of the survival of the second times the third times the fourth. Now, since each of these probabilities are the same thing, what we can do is just say the probability of one of them to the power of 4. And that's what I'm going to do here. That's how I would put it in my calculator instead of saying 0.99186 times that again, and then again, and then again. Just put into your calculator 0.99186 to the 4th power, and that will get you the same thing, which is 0.9678. And that is our probability for all 4 randomly selected 60-year-old females surviving that year. All right, so here is our third objective in this section 5.3. It's computing at least probabilities. And the example that I have here for you is similar to the previous one. It says the probability that a random selected female age 60 years older will survive the years, the same percent that we've looked at. What is the probability that at least one of 500 randomly selected 60-year-old females will die during the course of the year? Instead of it saying survive the course of the year, it says the opposite. So that is why we're saying compute the at least probability. So at least one of the 500 will not survive. Okay, so this is how you would compute that with the at least probability. So the probability that at least one dies, sorry for the morbidity here on this problem. It's just a problem that came with this lesson. Okay, it is equal to 1 minus, y'all remember doing the complement of a probability. This is the same thing that you would do here, is you'd find the complement that all 500 will survive the year, okay? So 1 minus that the probability of all survive. Okay, and since all of them are this same percent here, since all 500 are that, what you would say is 1 minus the probability that all 500 will survive. So the 0.99186 to the power of 500. Find this, subtract it from 1, and what you will end up getting is this number here. 9832. And there you go. That is how you compute an at least probability. Before we move on to section 4, I just want to go through some of the probability rules that we have looked at. And the first one here says the probability of an event must be between 0 and 1. If we let E denote an event, then this right here, this statement right here, is what we are stating. This is what is true, that our probability of an event is somewhere between 0 and 1. It's not going to be less than 0. It's not going to be greater than 1. And then the second rule here that we have learned is that the sum of all the probabilities in a certain sample space must be equal to 1. And that is if the sample space here is given, so a certain amount of events is given, and we take the probability of each one of those events and add them up, it should equal 1. The third thing we have learned in this chapter is that if E and F are disjointed events, then how we compute their probabilities is this right here. The probability of event E or F is equal to the probability of E plus the probability of F. And then if E and F are not disjointed events, if they have some commonality between each other, this is how we find the probability of that. We would say the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. Okay, now the fourth thing that we have looked at in this chapter is something called the complement of our event. So E represents an event, and E to C represents the complement of E. So that's how you would read that, complement of E. Then this is how you find the probability of the complement of E. Is this right here. It's equal to 1 minus the probability of E. And this is just the last thing that we have discussed, something about independent events. So if E and F are independent events, then we apply the multiplication rule. So if we have P of E and F, it is equal to the probability of E times the probability of F. All right, so now we're going to look into stuff that is in section 5.4, conditional probability and the general multiplication rule. And here are our objectives, computing the conditional probabilities and also compute probabilities using the general multiplication rule. So the first objective, I have an example for you on compute conditional probabilities. But first, let's figure out what a conditional probability is. So the notation, this right here, if you see this written somewhere, it means this right here, it reads the probability of event F given event E. So probability of F given event E. It is the probability that the event F occurs given that the event E has occurred. So these two probabilities, they are not independent. They go together with each other. So here's just a little intro to the conditional probability, how we use it. Let's look at this first question. It says, suppose that a single six-sided die is rolled. What is the probability that the die comes up 4, like the number 4? And so for this one, how you would find the probability to this is just how you would think, how we've done it before in class actually, is, okay, on a six-sided die, here's the sample space, numbers 1 through 6. And the probability that our roll is a 4, so the probability of rolling a 4 is equal to 1 out of the whole 6. So 1 out of 6. Now let's look at this right here. It says, now suppose that the die is rolled a second time, but we are told that the outcome will be an even number. What is the probability that die comes up 4? So here is our sample space in the second roll. Since we know that it's going to come up as an even number, out of 6 numbers there, only 3 of them are even, 2, 4, and 6. Now, what is the probability that an even number is rolled here, or our die comes up 4 now? Well, there's one of the 4s. Our probability of 4 now is 1 out of 3. So that's just a little introduction to conditional probabilities. If we know for a fact that we're only going to roll an even number, then we have a greater chance of rolling that 4 that we are expecting or wanting to have. Okay, so that right there is how conditional probabilities kind of work out. So here's our conditional probability rule. So if E and F are 2 events, then the probability of event F occurring given the occurrence of event E. This is how we compute it. We'll find the probability of E and F and divide it by the probability of E. Or you can do this. You can say the number of outcomes of E and F divided by the number of outcomes of E. So we don't necessarily have to compute the probability of E and F and then divide it by E, or the probability of E. We can use the number of outcomes to help us in finding the probability that we are looking for. But I'll have 2 examples for us, one showing us that we can use the number of outcomes to help us in computing this conditional probability, and then another one where we use probabilities to help us in computing the probability rule here. Now there's a table on your page to go along with this, and I have the table on the next slide, but here is what the table is all about. It's a survey was conducted by the Gallup organization, conducted in May 8th through 11th, 2008, in which 1,017 adult Americans were asked, which of the following statements come closest to your belief about God? You believe in God, you don't believe in God, but you do believe in a universal spirit or higher power, or you do not believe in either. So the results of the survey are here. And in the first example here, for using this table, we are asked, what is the probability that a random selected adult American who lives in the East believes in God? So I'm going to write out what exactly this is asking us to find according to the conditional rule. So we're asked to find the probability that um, this person believes in God, given that they live in the East. Okay, so using that rule there, I'm going to be looking in this row here because this is everyone that is in the East that was asked this question. And then now we're going to use those numbers along with the ones that believe in God to help us in computing this probability. So how we do this is that it's going to be the number of people that believe in God and live in the East. So this number right here, 204, believes in God and lives in the East, over the number of people who live in the East. So take the numbers that we have up here, and the number of people who believe in God and live in the East is this 204. 204 divided by everyone who lives in the East. So this whole row added up together, 204 plus 36 plus 15. And compute that, and you have your probability. So let's see, that ends up being 0.8 or 80%. And there we go. That is our probability for this first question. All right, so the way we're going to compute this probability is this way here. So we're finding the probability of they live in the East given that they believe in God. So in this first one, first portion of this probability, it's the same number as before, this 204, because the number that believes in God and lives in the East is that same amount. But then we put it over the amount of people who believe in God, the total number of that, which is this column. All right, so this right here, computing, it's not lie, lives in the East and believes in God. You don't have to write all of this out. I am, just for further explanation reasons. Okay, and then that really was supposed to be an N there. Sorry, guys. So N, it's not the probability we're using, it's the number that we're using. And then number of people who believe in God. Okay, now this, we take exactly what I said, 204 over the total column here, add it up together. 204 plus 212 plus 219 plus 152. And that computation there gives us 0.26. or you can say 26%. There you go. That is that probability. All right, here another example. We're going to be using, again, the conditional probability rule. Here, again, sorry that these examples are kind of morbid, but it's what I could find and use for this class. So here we have, in 2005, 19.1% of all murder victims were between the ages of 20 and 24 years old. Also in 2005, 16.6% of all murder victims were 20 to 24 years old males. What is the probability that all random selected murder victims in 2005 was male, given the victim is 20 to 24 years old? Okay, so what we have here is this probability that I'm about to write out. We are looking for the probability that the murder victim is male, given their age is 20 to 24. And this is how we find it. We are going to take the probability that they're male and their age is 20 to 24 and divide it by the probability that they are 20 to 24. And that is how you would find the probability that a random selected murder victim was male, given that the victim is 20 to 24 years old. Okay, so we take the numbers that we are given to us up here and we state this. So the probability that they're male and their age is 20 to 24 is this number right here. So put that in decimal form. And then the probability that they were just between the ages of 20 and 24 is the 19.1%. Divide those two numbers and you get this. Or you get this right here. I'm just going to round it to 3 decimal places. Or you can state this here, that it's 86.9%. There you go. So that is the probability for this one right here, that the person was male, given that they are ages 20 to 24. All right, so in Objective 2, we're going to be computing probabilities using the general multiplication rule, and this is the general multiplication rule. So the general multiplication rule is the probability that two events, E and F, both occur is given that you take the probability of E and F, and it's equal to the probability of E times the probability of F given E. And this right here is actually the same thing as what we have looked at in the conditional probability rule. I'm going to go back to that. See, the conditional probability rule, it's the same probabilities are all being used, except to find the probability of E and F, we just multiply both sides by this value right here, and we get our general multiplication rule for finding the probability of E and F. So not much is changing, just the way the, I guess, equation here is set up. So back to here, we're going to use this general multiplication rule in our next example, our last one also. Our last example here deals with murder victims again. And it says, in 2005, 19.1% of all murder victims were between the ages of 20 and 24 years old. Also in 2005, 86.9% of murder victims were male, given that the victim was 20 to 24. So this is what we had just figured out. We just found that this number, and we were given this, and also another probability. And what we're going to find here in this one is, what is the probability that a random selected murder victim in 2005 was a 20 to 24-year-old male? So let's look at this right here. This is the probability that we are trying to find. Trying to find the probability of that a random selected person was male and they were in between the ages of 20 and 24. So to find that, we're going to do this. We're going to be multiplying together the probability of victims who were 20 to 24 to the probability of the victims who were male, given that they were ages 20 to 24. Okay, and so we are given that up here again. Here's all of them who are between ages 20 and 24, and then here is the ones who are male, given that they are 20 to 24. So multiplying those together, we get this times the 86.9, and whenever we multiply that together, we end up getting this here, approximately. Whoops, didn't add it in a decimal number. There. And that is the probability that they're male and 20 to 24. Sorry, didn't mean to write and again. Just meant to write this. So that is equal to the 16.6%, which is the same number that we are given in the previous example. If we go back and look at it, let's go back and look at it. See? So probability that they're male and ages 20 to 24 was 16.6%, which that is the amount that we should have arrived at in this next example if we were doing everything correctly, which we did. So that is actually all I have for you. I will see you all in class. In class, we're going to be working on our assigned problems for these two sections. So be ready to do this. Goodbye, everybody, and hope you have a good weekend.